So note down this data. A retardation test is carried out on 1000 RPM. So normal speed is 1000 RPM. Decimation, the time taken for the speed to fall from 1030 RPM to 970 RPM. So he has given the conditions. So in first condition 36 seconds with no excitation. Second 15 seconds with full excitation. Third 9 seconds with full excitation, and the armature supplying an extra load of 10 amps at 219 volts. So calculate the moment of inertia of the armature in kg meter square, iron loss, and the mechanical losses at the mean speed of 1000 RPM is considering. Okay, so with respect to this data, so we have to go for stating some conditions. Okay, so during the first condition with no excitation, when there is no excitation, so the kinetic energy, so whatever the kinetic energy we are considering, so we will be considering only the mechanical losses, so not the iron losses in the first case. So in the second case, so with full excitation, so which includes both mechanical as well as the iron loss. So here we'll be finding what is the stray loss, and by using the third condition, so we can find what is the loss, and we have to find the moment of inertia, mechanical losses, and iron losses. Okay, so now with respect to this, so first let us go for this formula. So first you write W is equal to 2 pi by 60 square in into dn by dt. So just not dt1, so go for dt as the normal equation. It is the rotational loss equation. Have you written? Have you written that formula?
Yes, sir.
Yes, sir.
Okay. So now with respect to that, the first time period he has given as 36 seconds with no excitation. Okay, so what is the difference with respect to the speed? So it is 1030 minus 970, so we'll be getting around how much?
60
60
RPM.
60
60
RPM are
RPM.
getting. So difference with respect to time is 36 seconds. A normal speed is 1000 RPM. So substitute that in equation, say that as equation 1. So that is W is equal to 2 pi by 60 whole square in into dn by dt. So there you are substituting for mechanical losses. Are you getting? Next, similarly, let us go for the second condition. So which includes the stray loss. That is both mechanical as well as the iron loss comes into consideration. So with respect to that, so again the same expression, that is W. So for first condition, go for mechanical loss. So Wm you represent. Wm is equal to 2 pi by 60 square into in into dn by dt. So dn is 60 and dt is 36. So that say that as equation 1. Next, for second condition, for 15 seconds with full excitation, so both mechanical as well as the iron loss comes into consideration, that is stray loss. So Ws is equal to same, so 2 pi by 60 whole square in into dn by dt. So here dn again, it is difference with respect to speed is 60 and difference with respect to time is 15 seconds. Got it? So represent that as equation 2. None? Any doubts? Any doubts? Hello? Do you have any doubt?
No, sir. No, sir.
Okay, so stating that equation 1 and equation 2. Now let us go for the another equation. Also we know that is W rotational loss will be equal to W dash. So what is W dash?
V
That is
into
the
I.
additional loss. Okay, so W dash is the additional loss, that is V into IA. So V into IA, that is the W dash into T2 by T1 minus T2. That is the another formula what will be using for rotational loss. So why that is required? Because we have to know what is this stray loss. So we don't know mechanical loss, we don't know stray loss, right? So by using this equation, we can substitute W dash. W dash is equal to V into IA. So V is 219 volts and IA is 10 amps, right? So what is W dash value you are getting?
2190, sir.
Okay, so 2190 is the W dash. Now, with respect to the third condition, that is 9 seconds with the full excitation and the armature supplying that load, we are considering. Okay, so now what is T2? T2 by T1 minus T2. So T2 is 9 seconds and T1 will be 15 seconds with full excitation. Are you getting? So T1 will be 15 and T2 will be 9 seconds. So now you can find what is rotational loss. So now W is equal to W dash, that is a stray loss, is equal to W dash into T2 by T1 minus T2. So how much you're getting stray loss? That is W.
5475.
No, you're getting
3285 watts.
3285 watts.
3285.
3285, sir.
So 3285 watts. So now substitute that value in case of stray loss. So WS is equal, that is equation 2. So equation 2, what we have written, WS is equal to 2 pi by 60 whole square into I into N into dN by dt. dN is 60, dt is 15 seconds. So there you substitute 3285 W value and find what is I. N is 1000 RPM. N is 1000 RPM. So what is the value of I? How much are you getting?
49.97, sir.
Pardon?
49.97.
The value of I.
Yes, sir.
So
No.
75.
So it will be 75 kg meter square. Please check it out once. So I told you to substitute in equation 2. So equation 2 is Ws, which is equal to 2 pi by 60 whole square into I into N into difference in the speed is 60 and difference in the time is 15, not 36. Are you getting 75?
74.90.
Okay, fine. So consider it as 95 itself. Done? Any doubts? Now we have to find what is the mechanical loss and iron loss. Okay. So equation 1 is the mechanical loss. So equation 2 gives the total stray loss. So now divide equation 1 by equation 2. So if I divide equation 1 and equation 2, so that is Wm by Ws. So we know what is the value of Ws, or whatever the I you have got, you substitute in equation 1. So you can get what is the mechanical loss. So 2 pi by 60 whole square gets cancels. I and I gets cancels. Speed get cancels. So only 60 by 36. So dn by dt, and here dn by dt, that is 60 by 36 and 60 by 15 you'll be getting. So 60 and 60 gets cancels. So 36 and 15 will be represented in the equation. So mechanical loss will be equal to, so stray loss into whatever the difference with respect to the time. So that is 15 by 36. How much you're getting mechanical loss?
So 1369.
How much?
Sir, 1369.
1369 is the mechanical loss. Are you getting? Now once if I get the mechanical loss, I can find the iron loss. So stray loss will be equal to mechanical loss plus iron loss. So stray loss is 3.285 and mechanical loss we are getting, what is the value? 1369. So you differentiate this, that is difference, you take the difference, so you'll be getting 1916 watts as your iron loss. Are you getting? How much you're getting the mechanical loss? 1916 watts you're getting? Are you getting 1916 watts? Hello?
Yes, sir. 1916.
Okay, everyone are getting 1916 watts.
Yes, sir.
So that completes the model 2. So do you have any doubts with respect to this? Any doubts? Do you have any doubts? Hello?
No, sir.
Okay, so I'll go for the next model. So I'll stop the presentation. So next, let us go for another model. Model 4 I'll start. So instead of starting model 3, so I'll go for model 4. So that is a bit easy compared to model 3. So that is model 4, starting and speed control of induction motor. Is the presentation visible?
Yes, sir.
Yes, sir.
Okay. So while coming to the starting, so there are various methods of starting the induction motor. Okay. So why we have to go for the various methods? So what is the necessity of the starter? So generally when I go for the power equation, so power will be equal to root 3 VLIL cos phi. So that is one equation. The second, when I go for the rotor current equation, so I2 is equal to S into E2 by square root of R2 plus S into X2 square. Okay, so with respect to relating these two equations, so their line current will be equal to the power rating whatever for the motor, the capacity divided by root 3 VL into cos phi. So there if you see the voltage, whatever the power, it is a constant. So again root 3 and the line voltage is constant. So there the power factor comes into consideration. So during starting, so the power factor will be low. Okay, so it will be around 0.2. So generally would have been conducted a load test on a 3-phase induction motor. So while conducting, you would have been seen. So what was the F1 and F2? The difference was 0. And while applying the load, so we will be applying gradually. Okay, at the starting, a small load you will be applying. So then you would have been seen what was the value of the power factor. So it would have been around 0.2 or 0.3 or between 0.2 and 0.4 would have been your power factor. Okay, so with respect to that, generally since the denominator having a lower value, the current which will be flowing in the line will be having more. Okay, so to limit that current, we have to go for the starters. So not only with respect to that, so even with respect to the rotor consideration. So what is the EMF which will be induced? So again, the rotor EMF depends upon the slip of your induction motor. So as the slip at the starting, okay, so it is very high. So as the speed is 0, the slip will be maximum. That is almost near to unity. So once the motor has been started, almost we'll be getting some value of this slip. So due to that induced EMF, which is large at the starting, may damage the rotor conductors because the rotor conductors have been short circuited. So due to that short circuit, the large induced EMF will flow in the rotor circuit. So therefore, the rotor conductors may damage. So in this regard, so we used to go for the starters. So generally during starting, the induction motor may take 3 to 5 times the more the value, or 5 to 8 times more its rated value. So to limit that current, we are going for the starters. So that's the requirement of the starter. So not only with respect to that, so due to this heavy inrush of current will damage the stator windings also. So to limit that, we are going for the starters. And with respect to this, so generally once the motor has been started, so the starter will be totally disconnected. So generally it will be running at the normal voltage. So during starting, the voltage will be reduced so that the current also will be reduced. So with respect to that, the starters are required. So generally when the system, the load has been more its capacity, so then the starter will come into consideration, so that it can limit, or it can discontinue the supply when the motor has been overloaded, or if there is any fluctuation with respect to the voltage, then also the starter may limit the starter may protect the induction motor. So that's the another purpose of the starter. So now with respect to this starters, that is the necessity of the starter. So to limit the high starting current during supplying or during starting the motor, and for a short period the rotor gets accelerated and the motor will be running under normal condition with the normal voltage. So coming to the different types of starters, so based on the stator we are having starters, so based on the rotor we are having the starters. So generally as we see the expression, that is the rotor current equation, so E2 comes into consideration, that is the rotor induced EMF. To reduce that rotor induced EMF, so we can add the resistance at the starting, that is the rotor resistance, to reduce the current. Not only with respect to that, so also we have seen the slip ring induction motors. The slip ring induction motors where the rotor resistance has been included in the circuit. So it can be used for both controlling the speed as well as during the starting purpose. We can use the resistance. So while coming to the different types of methods, starters, there is a stator resistance starter, so star delta starter, direct online starter, that is a DOL starter, auto transformer starter, rotor resistance starter. So all these starters you can see in our lab. So already the rotor resistance starter, we have done some experiments. There is no stator resistance starter, but instead of that we are going for the auto transformer starter. So when you go for conducting the second cycle circle diagram, so there we will go for using the auto transformer. So the, or else in previous lab also we would have been done by using the auto transformer, the purpose of auto transformer. So now the load test for what we are conducting, it is a star delta and it's a direct online starter. So let us see how these starters will be constructed and what is the purpose and what will be the expressions with respect to the starter. So now let us go for the first stator resistance starter. So in case of stator resistance starter, so if you see here near the supply, we are connecting the 3 resistance to the 3-phase system, which is connected to the stator of an induction motor. So here to reduce the voltage, the resistance has been added in series with respect to your circuit. So initially these resistance are in maximum position. So that's why here he has given at the starting, here at the running. the resistance, variable resistance will be maximum during the starting. So once the supply has been given, the resistance, three resistance are simultaneously reduced. That means getting it to cutout position so that smoothly the current will be injected in the stator circuit. So the high inrush current can be reduced. So this is the schematic diagram of a stator resistance starter. Now with respect to this, what will be the torque at the starting and what will be the torque during the full load condition, that we have to take into consideration. So with respect to the X as the factor, so there will be some change in the voltage, so while varying the resistance. So considering that as the X as the factor, so let us see what will be expression for the torque. So now as we see the torque expression, so that is the relation between the starting torque and the full load torque. Let us consider the power, which is the product of torque and the angular velocity. So the torque produced and the power in the rotor circuit at synchronous speed. So torque is directly proportional to the power. P2 is equal to PC by S. PC is nothing but the copper loss. So copper loss in the three-phase circuit will be 3 times I square into R. So here the current and resistance, what we are considering with respect to the rotor. So therefore 3 into I2 R square into R2 into S. So here the resistance is constant and 3 is constant. So power is directly proportional to the current and the inversely proportional to the slip. So the torque is directly proportional to the current and inversely proportional to the slip. So now with respect to this starting torque and full load torque, if we consider, so what will be the expression? So here the rotor current and stator current at through the transformer action. So torque is directly proportional to I1 square by S. This is with respect to the stator. So where I1 is the stator current. At starting, slip will be equal to 1. So the torque at starting will be equal to I start square. So this is, say, consider this as equation 1. So now once the motor has been started, that is when the stator resistance is being used. So let us consider X as the factor where some starting current is proportional to this factor. So ISC is the normal current drawn under full load condition. So I start will be equal to X into ISC. So now the torque, starting torque is directly proportional to substitute for the starting current, that is X times the starting current. So full load current is directly proportional to IFL by SF, where SF is the full load slip. So considering these two equations, so equation 3 and equation 4, so we can represent, so what is the starting torque and the full load torque. So the ratio of starting torque to full load torque will be X factor, that is the voltage reduction comes into consideration, that is transformation ratio. So IS by IFL whole square into SF. So this is your expression for stator resistance. So this method is not much used, but still we have to remember the equation for starting torque to full load torque. So please note down this equation, or just you note down this equation, so which will be more helpful for solving the numericals. Have you noted down? So, and also make a note, as X is less than 1, the starting torque reduces by the fraction X square due to the stator resistance starter. Have you noted? Excuse me. Do you have any doubts? Do you have any doubts?
No, sir.
So let us go for the second starter, that is the star delta starter. So already this you would have been studied in your basic electrical. Okay, star delta starter. So initially the stator winding, that is which is been connected in star, is connected to the three-phase supply of R phase, bi phase, and B phase, and the finishing ends. If you see all these three finishing ends, generally this data consists of 6 terminals. So 3 starting terminals and 3 finishing terminals. Starting terminals are connected to the supply, and finishing terminals will be connected to the switch here, that is TP-DT switch. So here TP-DT switch will be switched to 2 positions. So during starting position, this will be connected in star. Here all the 3 terminals are shorted. So when all the 3 terminals are shorted, it will be connected in star. Once the motor has been started, so this switch will be switched to the delta connection. So that's how the connection will be made in case of star delta. So during running, it starts running in delta connection. So during starting, what happens? Your voltage gets reduced. So when the star connection, so voltage get reduced. In delta connection, the current gets reduced. So this is the construction of a star delta starter. So that's what here the explanation has been given. So it is used to reduce the voltage during the starting. So to reduce the current without using the external devices, so here consists of TP-DT switch, so which stands for triple pole double throw switch. So changeover takes place stator winding from star to delta during starting condition. So based on the switch, so how the current and torque equation comes into consideration. So here is the representation for voltage, how it has been reduced. So starting torque in the stator connected stator winding and starting torque in delta connected stator winding. So what is the voltage which will be represented in star? It will be VL by root 3. And here it is delta, line voltage will be equal to the phase voltage. So whole square if you represent, so with respect to that, so it will be equal to 1 by 3. So generally the starting current in the star delta starter will be 1/3 of its value. So the star delta starter is equivalent to the auto transformer starter with the tappings of 57.7% of tappings. So this is how your voltage will be reduced when I go for the star delta starter. So it's a simple construction. So please remember, here we are going for DP-DT switch. So 6 terminals, first 3 terminals will be connected to supply. The finishing terminals will be connected to switch. Here the switch will be in turn in delta connected. Okay, so finishing terminals. So here we have to change the phase. Do you have any doubts? Any doubts with respect to star delta connection? And please note down this equation. In case of star, the voltage is reduced, that is the starting torque, to 1/3 that produced by the dual starter. Okay, so next we'll go for the dual starter. That I'll do in the tomorrow's class. So how this equation has been represented? So based on the torque equation. Okay. The starting torque of an induction motor is proportional to square of the voltage applied to the winding per phase. So based on that, we are representing the starting in star and delta connection. Any doubts?
No, sir.
So this is with respect to the star delta connection. So tomorrow let us go for delta winding. So while coming to the advantages of star delta starter, so just it is an inexpensive. So generally it will not have much a complicated circuit. So efficiency is more, and it is available in the market. But only the disadvantage, the starting torque is reduced to 1/3 of its full load torque. So that is the one disadvantage. So applications wherever there is a induction motor, that is a 3-phase induction motor is being used. So in all there we are using the star delta starters. So maximum. So that is the advantages and disadvantages with respect and the applications of star delta starter. So next let us go for dual starter. So that this I'll take tomorrow. Any doubts with
No,
respect to
sir.
this? Okay, so this is your fourth model. Okay, so directly I'm going for